When performing acid-base titrations, it's important to use the correct indicator depending on what you're working with. These are the 4 possibilities. The indicator is chosen such that the pH at the endpoint, that is the point in the titration, when the indicator just changes color, matches as closely as possible to the pH at the equivalence point of the titration, that is the point where the acid has stoichiometrically reacted with the base. Since indicators change color over a narrow pH range rather than at an exact pH, it's important to achieve a close match of the equivalence point with the indicator's pH range. So here's our top 3. It's also important to realize that you're trying to match the transition color when comparing it to the equivalence point. So if you're using methyl orange and your endpoint is yellow, you've gone too far. You want an orange color. Essentially, indicators are just weak acids and can be represented like so. HIN is the unionized form of an indicator, and IN negative is the conjugate base. This equilibrium is influenced by changes in pH, so when the pH is low, as in more hydroniums, it shifts in the reverse direction to counteract the change and results in more HIN, which is essentially a particular color. Its conjugate base would have a different color as well. So during acid-base titrations, the pH of the reaction vessel changes over time. If we're adding base into the acid, the pH would change from low to high. Graphing these changes gives us these curves, so let's look at each of these scenarios. Strong acids and strong bases are completely ionized, so the neutralization reaction involves the hydronium ion and the hydroxide ion. The salt produced doesn't hydrolyze to any appreciable extent, so it has no effect on the pH, and therefore the pH of the equivalence point should be 7. If we kept adding equal concentrations of 0.1 mol per liter of sodium hydroxide to 10 ml of hydrochloric acid, the graph should look like so. Notice there's a rapid change from pH 3 to about 10, just with one drop. This means the equivalence point is around pH 7. Bromothymol blue would be the best to use as its endpoint is close to the equivalence point, so when the indicator changes from yellow to green, you're good to go. The pH at the equivalence point of a strong acid weak base titration is less than 7 because of the hydrolysis of the acidic salt produced in the reaction. If we took equal concentrations of 0.1 moles per liter of hydrochloric acid and ammonia solution, it produces the ammonium chloride salt. The ammonium ion is a weak Bronsted-Lowry acid and hydrolyzes in water to produce hydronium ions, which decreases the pH of the reaction vessel. Once again, if we kept adding equal concentrations of 0.1 moles per liter ammonia solution to the 10 ml hydrochloric acid, the graph should look like this. The equivalence point is roughly 5.3, so bromothymol blue could also be used. The pH at the equivalence point of a weak acid strong base titration is greater than 7 because of the hydrolysis of the basic salt produced in the reaction. For example, if you took equal concentrations of 0.1 mol per liter acetic acid and sodium hydroxide, the salt that forms will be sodium acetate. The acetate ion is a weak Bronsted-Lowry base and hydrolyzes in water to produce hydroxide ions, which increases the pH of the reaction vessel. Like before, if we kept adding equal concentrations of 0.1 mol per liter sodium hydroxide solution to the 10 ml acetic acid, the graph would look like this. The steepness is roughly between 7 and 10. So phenolphthalein could be used. So when you go from clear to a hint of pink, you've hit the endpoint. This little bit right here is the buffering effect on pH as base is added to the acid. Well before the endpoint, the solution contains both weak acid and its conjugate base. The pH rises only slowly in this region. Now the final scenario is for a weak acid, weak base titration. When acetic acid is titrated with ammonia solution, there is no rapid change in pH even at the equivalence point. The pH at the equivalence point is 7. As a consequence, no single indicator will achieve a sharp endpoint. Titrations of weak acids and weak bases are therefore best to avoid.